talking about physical properties and intermolecular forces and how functional groups kind of dictate the intermolecular forces that are present and that are possible. And we left off with this example. I don't know if we finished it though. It says rank the following order of decreasing melting point. So from the highest to the lowest. And again, the way we do that is the physical property itself. The stronger the physical property, the more effect it's going to have on, the stronger the intermolecular force, the more influence it's going to have over the physical property. So you would expect that something that's held together by hydrogen bonding would have a higher melting point than something that's held together by simple van der Waals interaction. So we went through and we looked at each one of these and we said that the alcohol it had van der Waals, it had dipole, and it had hydrogen bonding. Is that right? And I kind of went and explained what hydrogen bonding is using the OH group. So the hydrogen on one oxygen, the other another oxygen, and another molecule of that same alcohol is attracted to that hydrogen. So they kind of form a interaction between one of the lone pairs on that oxygen and the hydrogen atom that's there that I have depicted. As it's the strongest of all of your intermolecular forces on a covalent level. Right, the ionic electrostatic interaction is the strongest out of all of them. But on a covalent level, between dipole, or between van der Waals, dipole, and hydrogen bonding, this is the strongest. All right. So let's go back up here. Which one of these do you think is going to have the highest melting point? Right. This is van der Waals and dipole. This is also van der Waals and dipole. So which one is going to have the highest melting point?
The alcohol.
The alcohol. It's got the strongest intermolecular forces between it. And even though all of these are probably liquids, it's just a concept that I'm trying to make the point with. And I think I said on Friday that we could compare the fluorine and the ketone and determining which one had the strongest dipole. Did we talk about that? Somebody gave me or somebody had toward the end of class that gave me that answered the question that I asked. How could we determine which one had the strongest dipole? What can we measure? Like we have a way to determine. Let me back up. What is the dipole measurement?
It measures like the I think like the affinity of like an atom, or like electronegativity for it to like attract electrons if it's like stronger than another atom in the molecule.
So it's a measure of polarity.
Yeah.
Mm-hmm. So and then how do we know how polar a bond is? How can we tell that? If we know the dipole measures polarity, how can we tell how polar a bond is, or how disparate or the electronegativities of the two atoms. How can we determine that? You're right. Well, we have a way to do that, right? Can we just take the difference in electronegativities? So for this one, delta EM would be 3.5 minus 2.5. Is that right? This is oxygen, that's carbon, so it'll be 1.0. And then over here, that's F, that's C. Is that right? So if you had to estimate which one of those had the stronger dipole, which one would you choose? Based on the difference in electronegativity of the atoms.
Would we choose the 1.5 one?
Sure. So the difference in electronegativity is bigger, so the dipole is also going to be bigger, right? So if we're comparing that fluoride, the alkyl fluoride to the ketone, which is on the left side, far left side, and we're saying the stronger the intermolecular force, the more influence it has over the physical properties. Can we make the assumption that that stronger dipole is going to be is going to cause the alkyl fluoride to be a little bit more attracted to each other than the ketone? Can we make that assumption?
Yes.
Mm-hmm. So from that assumption, can we say that that is going to have a little bit slightly higher melting point than a ketone, based on the strength of that dipole-dipole interaction? Right, so when we're comparing, sorry about that. I'll write it down here. So comparing the I'm gonna number these. So we're comparing 1 and 3. Three is going to have a stronger dipole, so we can assume from that that it also will have a higher melting point. Is that logical? If it's not clear, just ask a question or say something. All right. The next idea that we want to talk about is solubility. Right. So with solubility, what we're talking about is right, a solute being dissolved, or if it's a solid, you dissolve it up, or if it's a liquid, it would be soluble. So a solute being dissolved up or being soluble in a solvent to make a solution. Right, for organic, there's a very simple axiom that we can follow to help us understand whether two things are soluble or insoluble, and that is like dissolves like. So if something is polar, it's going to dissolve stuff that's polar. Right? If a solvent is polar, it's going to dissolve up things that are polar. If it is non-polar, right, it's going to dissolve things that are non-polar. Right, and the other part of this that we want to talk about is water solubility. That's very important. Right, water solubility means can I dissolve something up in water, or if it's a liquid, are they miscible? So for a solid, right, we want to ask if it's soluble in water, and then for a liquid, we want to ask, is it miscible? Right, that's a different term. Right, if it's miscible, that means do the two liquids come together and make a solution. Right, everything is not miscible. So if it's immiscible, then you're going to end up with two layers. Right, so the classic way to see this is in what we call a separatory funnel. Again, my drawings don't make fun of that, but so you'll have in a separatory funnel, right? If the two solvents or the two liquids are immiscible, you'll have, let's just say, for the sake of argument, that the top layer is organic. And the bottom layer is water. Right? That's what it would look like if the two were immiscible. If they are miscible, then the water and the organic liquid will go together and they'll make one solution. There's a way to determine that miscibility as well, right? If we have an organic compound, there is if you watched the little sink or swim video, then you already know where I'm going with this. So how can we determine water solubility? Right? In order for an organic compound to be considered soluble in water, can somebody tell me, if you watch the sink or swim, or if you watch the other solubility video, can somebody tell me what the requirements are?
Is it for every 5 carbons, there must be one hydrogen bonding atom?
Yes, who was that?
Jamiria.
Excellent. So for every 5 carbons, you need one hydrogen bonding atom. Tell me what are the hydrogen bonding atoms? What atoms can hydrogen bond? Because everything can't, right? There's some 3 specific atoms that can hydrogen bond with water.
It's oxygen, nitrogen, and fluorine.
Mhm. So for these atoms are O, N, and F, right? In the video, I try to make it like a little mnemonic, HNOF, so heck no, fool, something like that. But just to help you remember that it's oxygen, nitrogen, and fluorine. So in order to determine water solubility, you have to meet this ratio. So for every 5 carbons, you need 1 hydrogen bonding atom. Right? That means if you have 10 carbons, you need 2. If you have 15 carbons, you need 3. If you have 20 carbons, you need 4, so on and so forth. But the ratio is for every 5 carbons, you need 1 hydrogen bonding atom in order for an organic molecule to be soluble in water. Right? So let's do this. Let me go back up top and grab some of these examples. We'll work this idea off of here. Let's grab this. Let's see if I can't erase it. That's okay. Let's look at this first one. And what we want to do is count up the carbons, and then we're going to count up whether there are oxygen, nitrogen, or fluorines present. And then we're going to determine whether or not the ratio is met and whether each one of these compounds is soluble in water. All right, so let's go to here. Let's count the carbons up first. I can't erase the highlights, so I'll just count them. So 1, 2, 3, 4, 5, 6, 7, 8 carbons. Right? Everybody okay with that?
Yes.
Now we're looking for N, O, or F. One of those 3 atoms, right? How many do we need if we have 8 carbons? If we need 1 for 5 carbons, once we pass 5,
2.
right, we got to add another hydrogen bond now. So we need at least 2, right? So we have here 1 oxygen, 2 oxygens, and then a nitrogen. So we have, I'm just going to call those hydrogen bonding atoms instead of listing them separately. So we got 8 carbons and we have 3 hydrogen bonding atoms. Is that right? So would you say that phenacetine is soluble in water or insoluble in water?
Soluble.
It's soluble. How many more carbons could we add and it still be soluble? Remember, it's the ratio is 5 to
7.
1. Yes. Did you say 7?
Yes.
Yeah, we can have up to 15 carbons here because we got 3 hydrogen bonding atoms. It's 5 to 1, 10 to 2, 15 to 3, and so on and so forth. So this is soluble. All right. What about acetaminophen? Let's do that one. Let's count the carbons up first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. And then we have now 1, 2, still have 3 hydrogen bonding atoms. Everybody okay with that abbreviation? HBA. Yes or no? Soluble or insoluble?
soluble.
It is soluble. All right. Okay, what about aspirin? Let's see what we have. 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. I'm sorry, 9 carbons. And then how many hydrogen bonding atoms? That's again, that can be nitrogen, oxygen, or fluorine.
4.
4. Good. So in this case, if the ratio is 5 to 1, or 10 to 2, or 15 to 3, or 20 to 4, right? How many more carbons could I add and this still be soluble? Say that again. Did you say 11?
Yes.
Okay, good. The reason I'm asking that is because when I teach this part, there's always confusion if it doesn't match the ratio identically. So if it's not identically 5 to 1 or 10 to 2, but in this case, you have less carbons than you have hydrogen bonding atoms. So it's guaranteed that this will be soluble in water, right? So it is soluble in water. All right, now let's do so it can be, the ratio can be up to 20 to 4, right? And it still be soluble. Or we can keep adding, right? 25 to 5, 30 to 6, so on and so forth. You can just keep adding. But if it falls anywhere in that window, then it's going to be soluble in water. Let's look at the next one. This is THC. We talked about this before. Let's count the carbons up. 1, I'll like that color. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 carbons. Is that right? Did I miss anything? So we got 21 carbons. And then how many hydrogen bonding atoms do we have? We got an oxygen right here. Let me use a different color. An oxygen here and an oxygen here. Is that right? Any other hydrogen bonding atoms present? Remember, that's nitrogen, oxygen, or fluorine. What do you think? Soluble in water or no?
No.
It is not soluble in water. Right? That's how many carbons would we have to subtract, or how many hydrogen bonding atoms would we have to add to make it soluble?
You can subtract 11 carbons.
Okay, good. 11 carbons, or how many hydrogen bonding atoms will we add?
3.
3. right? So you either subtract 11 or add 3. Most of the time with something like this, if you want to make it water soluble, your best bet synthetically is to add something to this alcohol right here. Add some other functional group that has some hydrogen bonding atoms in it. This is intriguing because like we looked at THC. We also looked at some point, I think we looked at CBD. Is that right? When we're looking at functional groups. Let me do that up here somewhere. Yes, I think, yeah, we did right here. Right. And so CBD is the same idea, right? It's not water soluble either, but they make water soluble versions of it. So I want to see what it looks like if we can find it. Because I know like with CBDs, you know, some of them are water soluble and some of them is just the oil. But let's see. Let's see what the structure is. Let's see how they modified it. If they show it. Or maybe it's a different CBD altogether. They probably don't have it characterized. That sucks. Might be on the sub. This is what I'm looking for right here, right? So again, when you think about, let me screenshot this and import it, if y'all don't mind. And this is again, when you think about organic, man, organic is so freaking amazing. You can do so much stuff. And there's so many different ways to do things. So let me put this up here. Let's see what they did. Right. So let's look at the CBD itself. Right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons there. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 carbons. You got 21 carbons, 2 hydrogen bonding atoms. Right. So we know that this is insoluble. We saw that with THC. Right. And we go over here, let's look at what they did. Because remember I said up here, the best way to solubilize something that's insoluble is not to take carbons away, because then you're going to change the actual molecule itself. But you can modify the oxygen. Maybe you add in another group or another functional group that contains more oxygens or more hydrogen bonding atoms. So let's see what they did. They added in an SO3 group, right, to both oxygens. To both oxygens. So that SO3, that functional group, the sulfonate, it actually looks like this. So you would have oxygen and then sulfur with a double bond here, double bond here, and an O here, And then that's a salt with sodium, so Na plus. You can see right there, the ONA, or the Na is a counter ion. So they make this a salt, and that also adds to its solubility, right? Because now it's very polar. So because it's polar and water is also polar, then you're going to have that working in your favor as well. And it's the same thing up here. All right, so O, S, that's negative. And then the sodium out here is positive, right? Again, this is organic chemistry on a practical level at work. So the oil that you get from hemp or from wherever you're deriving your CBDs or THC oil from, you know where you get that from, is insoluble in water, but it can be converted into molecules that are soluble. So these sulfonate salts that you see on the right, those are soluble in water. And now you got a whole different, you got a totally different delivery method, right? I don't know how many of you have actually taken CBDs. I've taken it before. The oil is sublingual, put 2 drops under, however many drops under your tongue. And I don't know if you've ever done that, but it's impossible to keep it there. You have to wait for several minutes for it to be absorbed, and it's impossible. But the water soluble is totally different. You can put that into a bottle of water, bottle of Gatorade, into your tea, whatever, and it's a game changer because now you got a different delivery method. It's more bioavailable, so on and so forth. So it changes everything. So water solubility is actually very important. And this is one of the ways that we can illustrate that importance, you know, by looking at how water solubility is connected to, you know, different biological molecules that may have health advantages, right? And that's why, again, up here, when you look at phenacetin and acetaminophen, that matters too, right? You think of if acetaminophen wasn't water soluble, what could you do to it? This is an off the record type of question, but what could you do to acetaminophen if it wasn't water soluble already? Where could you modify it? Anybody?
You could put, I guess, like a hydrogen right there with the oxygen by the
Okay. What about okay, so the oxygen, which one? The one in the amide or the one in the ether?
one in the amide.
Okay, so you want to protonate this right here. Okay, if we did that though, would it what would that change? Because it's difficult to add something to that carbonyl and for it to stay. It's not going to stay because the oxygen is going to become positive and it will rather be neutral. But if this wasn't water soluble, you can modify it right here at the nitrogen. Right, that's why I drew that long pair in. Nitrogen will be much more reactive. So you could do something there that would add in, or you can add in a functional group there if you needed it. That's a spot where you can modify it. The carbonyl oxygen and the ether oxygen, those are not really as reactive, but that nitrogen, you could definitely use that. You could take the hydrogen off of it and then add in some other functional group if it was necessary. All right. Any questions about water solubility? Any questions about the ratio of hydrogen bonding atoms to carbon? Any questions about what hydrogen bonding is? Anything? Okay. All right. So we actually have to have another handout. I don't know if I have it. I think I may have pulled it, but I can't remember. So the next section is dealing with pKa and acidity. And I don't have that handout available, but there's an example in here that I can use to at least introduce you to pKa. So let me do that. Let me go up to, I'm gonna grab it. And you know, this is not gonna be due. You won't have to turn this in, but this is let's see, yeah. This example right here. So I'm gonna put this on a new document, and then when I import the pKa document, I'll put it all together, so there won't be any confusion. Right, or actually what I'll do is I'll just add this question into the pKa document. So when you submit that, you'll be able to, you may have to modify that document to add this to it. I'll figure it out, and then I'll get it straight. All right. So when we talk about 9 minutes, we talk about acidity, right? That actually in GChem, you probably learned about 2 types of acids, right? And 2 types of bases. So Lewis, I'm gonna start out with Lewis acids. So a Lewis acid is an electron pair acceptor. And then a Lewis base is an electron pair donor. Right? Those are a little bit kind of really basic simplified definitions, but in the case of a Lewis acid, something like a cation will be considered a Lewis acid. Something with an empty orbital, like boron, it's got an empty p orbital, so it can take a pair of electrons. A metal, kind of like let me think of a good one. Titanium is a good Lewis acid, right? Your metals have d orbitals a lot of times that are empty, so they can take electrons. Right, and these are just a few examples. Lewis base, on the other hand, is an electron pair donor. So that would be anything with lone pairs like nitrogen, oxygen, especially if it's negative. But a carbonyl oxygen can also be a Lewis base. You can have a carbanion that can be a Lewis base. It's got a lone pair. So basically anything with a lone pair that can donate electrons is going to be considered a Lewis base. But when we think about acids, we learned in general chemistry about acids. We learned about Bronsted acids. Right, and that is an H plus or proton donor. Right, so something like HCl, like HBr, sulfuric acid, something like that. So anything that can donate a proton. And then we also learned about Bronsted bases. and those were H plus acceptors, right? Like nitrogen or right, or oxygen, especially in the hydroxide anion, that's a proton acceptor. Right, you can also have other types of bases, like the terpbutoxide anion, so on and so forth. So it depends on what the base is. The definition of a Bronsted base is that it's a proton acceptor, right? It can pick up H plus from an acid, right? But in CHEM, when we learned about acids and bases, we learned about how to determine acidity based on what we call Ka, right? The equilibrium constant for acid dissociation, right? We learned about so Ka would be the concentration of the products, H plus, A minus over HA. Anybody remember that from GChem? I think you probably studied it in part 2, dealing with the equilibrium constant of acids. But at any rate, when you think about an acid in the sense of general chemistry and not organic, most of these acids are spontaneous. So most of them, when you make a solution of them in water, they spontaneously dissociate. And what we also know is that you can look at the equilibrium constant and kind of tell what the acidity is by the value, right, or the magnitude. If Ka is a big number, what that means is that there's very little HA left over. Right? If Ka is a large number. If Ka is a small number, then the opposite is true. There's a whole bunch of HA left over and the acid didn't really fully dissociate. A lot of HA left. So this is indicative of a weak acid. So a weak acid is going to be not dissociate fully, and you have a lot of HA left over. So that's weak. By the same token, if the Ka is large and HA is small, and that means that most of it broke up into its components, then this is indicative of a strong acid. We're going to use this ideal concept of Ka to describe organic acids also. Because one thing about organic acids, not many of them dissociate readily in water, like if you're making a solution. And so you have to have a different way to describe them. And so what we're going to start talking about is what we call the pKa. And that pKa, and I just had a good pKa list. I'll make sure I have it in the next class. But the pKa is a way that we measure organic acids. All right, so non-organic acids we measure with Ka. When we talk about organic acids, we measure with pKa. But we'll talk about that on Wednesday, and I'll send a acidity video to you so you can prep yourself before you come, so we can just dive in and start working. All right, any questions? All right, if not, then we'll stop here and we'll pick up on Wednesday.